Hello and welcome to this Napatech tutorial. In this tutorial we will describe how the host buffer allowance function is useful in data sharing scenarios where multiple applications share the same received data stream. As you will see, data is shared between applications in a ring buffer. By assigning a host buffer allowance level for each application, multiple applications with different performance capabilities can share data in the ring buffer. The host buffer allowance level is defined as a percentage for each application and configured via the nt_netrx_open function. In the following example, we will describe a host buffer allowance scenario consisting of 3 applications. One application reads at full ingress rate, whereas 2 other applications read slower than the ingress rate. The slower applications read at a rate 2/3 and 1/3 of the ingress rate, and will only be allowed to occupy up to 25% and 50% of the host buffer respectively. We will show how the system eventually becomes blocked if the applications do not read sufficiently often from the same data stream. Each stage of the process described in this scenario is referred to relative to its real-time state. In other words, time 0, time 1, time 2, etc. The ring buffer is configured with 16 segments. 3 applications, application A, application X and application Y, are to share the received data. The most important recipient of data is application A and is assigned an allowance of 100% as it has to be capable of keeping up with the incoming traffic. The other 2 applications are not able to handle their activity at the incoming rate and will drop packets. They are granted an allowance of 25% for application X and 50% for application Y for their processing. Incoming traffic is not yet configured and the host buffer is empty. Incoming traffic is now configured and starts populating the host buffer. The writer moves ahead writing data to each segment. Application A and application X now subscribe to the received data stream and are given a pointer to the most recent available segment. The writer is working on the next segment. Application A and application X read as fast as they can, where application X is the slowest and cannot keep up with the received data rate. Application A processes according to the incoming rate. Application X has finished segment 3 and continues to segment 4, whereas application A has finished segment 4 and continues to segment 5, which has just been made available by the writer. Application A continues to follow tightly after the writer, and application X drops further behind, but still not blocking more segments than allowed. Segment 6, 7 and 8 are blocked by application X, which is only at a level of 18.75% and not yet beyond the allowed 25% host buffer allowance. At this time, a third application, application Y, wants to read from the same buffer, and when joining is assigned the most recently available segment, segment 8. Application Y is a slower application than the 2 others and has been assigned a host buffer allowance, allowing it to block up to 50% of the host buffer space. Application Y processes its data slowly and has only processed data from 1 segment, while the writer has filled 3 more segments. Application X is also slower than the writer and is now 4 segments behind. Application A continues to follow tightly after the writer. At this time, application X requests to read segment 10, but since application X is now blocking segments 10, 11, 12, 13 and 14, which is more than the allowed 25%, the segment that application X is assigned for reading will be segment 14, the newest segment. That means that the read pointer for application X is now moved to segment 14 instead of segment 9. Application Y has also only reached to segment 10 and is therefore blocking the same 5 segments as application X. But since application Y is allowed to block 50%, it will get the expected pointer to segment 10. Application A continues to follow close after the writer. As a result of the host buffer allowance process, application X will lose contents of segments 10, 11, 12 and 13, whereas application A and application Y are not losing anything. The writer has now filled 3 more segments. Application A continues to follow along, whereas application X has only reached to segment 16. Application Y is even further behind, is only at segment 11. Application A still follows right after the writer and starts reading segment 20, whereas application X starts reading segment 18. Application Y has only reached segment 12, but since the writer is now writing to segment 21, application Y blocks all the in-between segments, segments 12 to 20. Application Y is therefore blocking more than the agreed 50% for that application. This means that application Y will get a pointer to data in segment 20 instead of segment 12. Hence, at this time, the host buffer allowance function will result in application Y dropping contents of segments 12 to 19, whereas application A is still not losing anything. The flow continues and the writer has now filled 3 more segments, starting on the 24th segment. Application A continues to follow along, whereas application X has only reached segment 20 and application Y is at segment 21, since it has managed to read 1 segment since the force drop performed at time 7. The writer has filled 3 more segments and is starting on segment 27. Application A continues to follow along, whereas application X and application Y are slower. Application X and application Y both request to read their next segment, segment 22, but since application X is now blocking segments 22 to 26, which again is more than the allowed 25%, the segment that application X gets for reading will be segment 26, the newest segment. Application Y gets segment 22 as it does not yet block the allowed 50%. Hence, at this time, the host buffer allowance function will force application X to drop contents of segments 22, 23, 24 and 25, whereas application A is still not dropping anything. Application Y continues at its slower pace, reading segment number 22. The flow continues and the writer has now filled 3 more segments, starting on the 30th segment. Application A continues to follow along, whereas application Y has only reached segment 23 and application X is at segment 28, since it has managed to read 2 segments since the force drop performed at time 9. The writer has now filled 3 more segments, starting on the 33rd segment. Application A still follows along. Application X reads on at its own pace and has reached segment 30. However, application Y has run into an issue, for example, complex processing, a simple application error, or something else that stalls its processing, somewhere in segment 23 and is stuck there. While the problems continue for application Y, the writer fills the free available segments with new data. At this time, it has written 3 more segments and starts on segment 36. Application A follows along and starts in segment 35, while application X lags a bit behind and has only come to segment 32. The writer has filled 3 more segments. Application A follows along as expected. Application X is lagging behind by 5 segments, more than the 25%, and will be moved up to the most recently filled segment, segment 38. However, there are now no more free segments as segment 23 is still blocked by application Y, since it has not yet completed the processing of the data in segment 23. The host buffer allowance function continues processing and will force application X to drop contents of segments 34, 35, 36 and 37 and start reading segment number 38, which currently is the last available segment if application Y does not soon complete its processing of segment number 23. Application Y still hasn't completed its processing, meaning that it hasn't released the segment, so the writer does not have anywhere to store new received data, and data will be dropped at the ingress port of the system. In other words, the system eventually becomes blocked if the applications do not read sufficiently often from the same data stream. To conclude, the host buffer allowance function allows different applications or processing engines to share received data. However, the subscribing applications or processes must read sufficiently often to prevent the overall ring buffer filling up, blocking further incoming data.